All right, let's tackle the second half of our lesson on trigonometry. And in this half, we're going to talk about inverse trigonometric ratios. And probably the best way to describe these is to drop back to our special right triangle, our 30, 60, 90 triangle. Do you remember this guy? And we said that in a 30, 60, 90 triangle, if we call the short leg S, then the hypotenuse is 2S, and the long leg is S times the square root of 3. And so in our last lesson, we learned that we could take the cosine, find the cosine of 60 degrees. Cosine is adjacent over hypotenuse, so it was S over 2S, which we found was 1/2. Okay, and we also were able to find, we could find sine of, let's take the sine of 60 degrees. And sine is opposite over hypotenuse, so this was S square root of 3 over 2S, which simplifies to the square root of 3 over 2. And we were also able to find that the tangent of 60 degrees, from this we could find tangent is opposite over adjacent, so it was S square root of 3 over S, which simplified to the square root of 3. So basically, what inverse trig ratios allow you to do is to say that if the cosine of 60 degrees is 1/2, well, then if I told you I have an angle and its cosine is 1/2, you could tell me that angle must be 60 degrees. It just allows us to go the other way. If I have an angle and I told you that the sine of that angle was the square root of 3 over 2, you should be able to tell me that angle must be 60 degrees. So if we know an angle, we can calculate its cosine. If we know an angle's cosine, we can calculate the angle. That's basically what this is saying. And likewise, if I told you I have an angle and its tangent is equal to the square root of 3, you can tell me that angle must be 60 degrees. So this is how it's written. If the sine, let's talk inverse sine first. If the sine of angle A equals x, then the inverse sine of x is the measure of angle A. And one thing, this is a little bit archaic, but I'm going to tell you about it anyway because it might be helpful, and you're probably going to see it somewhere in a text along the line. When I was your age, this was not written like this. This was written as arcsine. Arcsine x equals the measure of angle A. And my trig teacher in high school taught me to just simply read this word arc as, quote, an angle whose sine is x. And so you may see it like that, but just realize that when you're looking for an angle, you're going to be looking to use the inverse trig function. Likewise for cosine, we would write it like this. If the cosine of angle A is x, then the inverse cosine of x is the measure of angle A. And you'll see in older text, you'll see that written as arc cosine. Arc cosine x equals the measure of angle A. An angle whose cosine is x, that's A. And we can also do inverse tangent. If the tangent of angle A equals x, then the inverse tangent of x equals the measure of angle A. And in older text, you'll see this written as arctan. Arctan x equals the measure of angle A. An angle whose tangent is x. That's what we're looking for. In some ways, I like this older terminology better because you don't have the same confusion with this problem right here. Make sure you realize that that's inverse function notation. Okay, it is not a negative exponent, so you want to be careful with that. That's inverse function notation, not to be confused with a negative exponent, which would imply that you would put 1 over the tangent of x. That's not what that means. Let's write that out right now. This does not equal 1 over tangent x. Not the same thing. That's not what that's all about. So, okay, let's take a look at a couple of examples. And we're going to be using our calculator on this, so you might want to have your calculator handy. You'll notice that in our last lesson, we looked at the sine, cosine, and tangent functions. If you want to access these inverse functions, you just hit the second function and hit those buttons to use the function that's going to help you find the angle. Let's try this guy right here. Could we use a calculator to find the measure of angle P to the nearest tenth? Now don't forget, this stuff is still important. So, ka and toa. Why do I need this? Well, I need it to figure out which of my inverse trig functions to use. When we're talking about angle P, and I know this and this, well, what sides are these with respect to angle P? I've got the adjacent side and the hypotenuse. Which trig function correlates adjacent and hypotenuse? That is cosine. So I'm going to want to use the inverse cosine. The first couple times you do this, you might want to write it out like this. I know the cosine of angle P is 13/19. Therefore, I could say 13/19. I'm looking for an angle whose cosine is 13/19, and that'll give me the measure of angle P. Okay? If you want, the first couple times you do this, if you want to write it out like this, and then switch it over into its inverse form, eventually it'll become kind of instinctive. Let's go ahead and see what we get when we put in second function cosine 13 divided by 19. Enter. And I get to the nearest tenth, we're going to get the measure of angle P equals 46.8 degrees. Okay? So don't forget, this is still important, so katoa, because you've got to pick the right trig function to use. Let's go ahead and try another one. Could we use a calculator to find the measure of angle D to the nearest tenth? Now again, I want to remember, so katoa, because with respect to angle D, what sides do I know? I know the opposite and the hypotenuse. Which trig function correlates opposite and hypotenuse? That's going to be sine. So I know the sine of angle D is 16/23. So the inverse sine of 16/23 should equal the measure of angle D. And let's go ahead and try that. Second function sine, to get me my inverse sine function, 16 divided by 23. Hopefully you guys can see that. And we get the measure of angle D is approximately 44.1 degrees. Okay? All right, everybody good with that? Let's see what else we can do here. Oh, excellent. This is when it gets fun. Solve the right triangle. Now, when you see this, don't forget every triangle has how many parts? That's right, it has 6 parts. It has 3 angles and 3 sides. So to solve the right triangle, we've got to find all 6 of those parts. It looks like we've got 1 angle and we've got 2 sides. So what do you want to go after first? How are we going to get side AB? Now, some of you are probably saying, well, let's just go with what we know. We know Pythagorean Theorem. You can do that. You can absolutely do that. But now, after these last 2 lessons, you have a shortcut that you can use. You could find this using one of your trig functions. If you're going to do that, you're going to need to know one of these angles, A or B. How could we find angle A or B here? Why don't we go ahead and go after angle A? Well, don't forget, so toa. With respect to angle A, I know the opposite and the adjacent. So I want to use tangent. The tangent of angle A is 4/7. So that means the inverse tangent of 4/7 should equal the measure of angle A. Now let's see what we get there. Second function tangent, 4/7. And we get 29 point, I'm going to round it to the nearest hundredth. Measure of angle A is approximately 29.75 degrees. Okay. Well, now that I know that, I could use a trig function to find x. Which one should I use? I'm looking for the hypotenuse, and I know both the opposite side and the adjacent side. So I could actually use either sine or cosine here. Which one do you want to use? Okay, let's use the sine. The sine of 29.75 degrees is going to equal 4 over x. Okay? And I'm going to encourage you to solve these for x before you grab your calculator. I don't know if you guys know this trick. I call it the numerator shuffle. I'm going to bring this numerator over here and say 4 over the sine of 29.75 degrees equals x. How can I get away with that? It's a shortcut that you'll use a lot in trig problems, so you might want to get comfortable with it. Really, what am I doing here? If I start out with this equation, the sine of 29.75 degrees equals 4 over x. In order to solve this for x, you might be inclined to multiply both sides by x. Okay, they'll cancel over here. And then I get x times the sine of 29.75 equals 4. So what do I do next to solve for x? Now I divide both sides by the sine of 29.75. And I end up right there. Every time. If you want, if you've got your variable in the denominator, you can shuffle the numerator over to this side. That's why I call it the numerator shuffle. Maybe I'll put that on the test. Numerator shuffle. Okay, it will save you a lot of time in doing these trig problems, because now that I have it solved for x, I can go ahead and say 4 divided by sine 29.75, and I can just put that right in my calculator, and I get 8.06. That's approximately equal to x. Okay. Let's see, 8.06. Now, if you wanted to, you could go ahead and check your Pythagorean theorem. It should work. 4 squared plus 7 squared should equal 8.06 squared. So we get 16 plus 49. Let me try that again. 16 plus 49. So if we take the square root of 65, we get 8.06. Look at that. It all works. Okay, so we're just missing one piece of our triangle right now. Now, it would be really fun to use angle B here. Maybe the sine of angle B equals 7 over 8.06, but we don't need to do that anymore, do we? As you zero in on the last piece of the triangle you're missing, you probably recognize the triangle sum theorem helps you get the rest of this. Or hopefully you remember the fact that the acute angles in any right triangle are always complementary. So 90 minus 29.75 gives us 60.25 degrees. And we've solved our triangle. All right, let's try another one like that. I know that was a lot to absorb. Let's try another example. Let's go ahead and solve this right triangle. Now, if you want to do Pythagorean theorem to start to find AB, there's no problem with that. We know that a squared plus b squared will equal c squared. And 8 squared is 64, 11 squared is 121, so we get 185. Let's take the square root of that, and we get about 13.60 approximately. Round side measures to the nearest tenth, so we'll call that 13.6. Okay, now how are we going to find these angles? We've got 1, of course. Shall we go after the measure of angle B? And you can use, because you know all 3 sides, you can use any trig function you want. You can use sine. Sine of angle B equals 8 over 13.6. Or you can use cosine. Cosine of angle B equals 11 over 13.6. Or you could use the tangent. The tangent of angle B equals 8 over 11. And why don't we go ahead and do tangent. If the tangent of angle B equals 8 over 11, then the inverse tangent of 8 over 11 should give me the measure of angle B. All right, let's try that. Inverse tangent 8 over 11. And we get angle measures to the nearest degree. So we're going to say the measure of angle B is approximately 36 degrees. Okay. If angle B is 36 degrees, what's the measure of angle A going to be? 90 minus 36 gives me 54 degrees. And there we've solved our right triangle. All right, that is trigonometry. Basically, from our trig functions to our inverse trig functions. Oh, and as promised, the world's funniest math joke. Okay. So we have a horse walks into a bar, and he says to the bartender, if you've got a right triangle, x, y, z, such that y is the right angle, which side is the hypotenuse? And the bartender says, y, the long face. Thanks, guys.